In previous lectures, we've considered a system which consists of only one locus with two alleles or with more alleles. So we considered Hardy-Weinberg equilibrium, which determines the distribution of genotypes in panmictic population. However, loci are located on the chromosome, and actually the loci, which are very close together, they are linked, and therefore frequently the statistical distribution of the genotypes between such two loci is statistically dependent. Michel, in one of the previous lectures, have been talking about biological basis of linkage disequilibrium, and have been talking about haplotypic blocks. So these blocks are defined in the mosaic from which our genomes are composed of. Now we are going to take this topic and give it a little bit more mathematical treatment. For that, we are going to consider a relatively simple system which is going to consist of only two loci, presumably linked together, and in each locus there will be possibility for two alleles, say A capital and A small for one of the loci locus, and B capital and B small for the second locus. Before we continue, I need to introduce you with one definition which will become very handy in further consideration. We say that two alleles coming from two different loci are in cis when these two alleles are located at the same chromosome. When we are talking about two alleles which are located at different chromosomes, we will call these alleles to be in trans. So now let's think of just two locations in the genome, and we start with this simple system where at the first location this locus is polymorphic, it has two alleles, while at the second location it is monomorphic in the population considered, so we only see B capital alleles. However, at a certain time point, a mutation may occur, giving rise to initially only one copy of the chromosome, which will have capital A at the first location and small b, the mutant B, at the second location. After some time, if this allele is in a way lucky, it may propagate in the population because of random factors such as drift. And then, after a certain time in the population, we can see the collection of three possible chromosomes, A capital, B capital, A small, B capital. These are the original chromosomes, and they're the chromosome and haplotype which arose because of mutation, which consists of capital A in one location and small b in another location. If these loci are relatively far apart, or a lot of time has passed, then there may be recombination between two loci, and in that, after some time, you may see that in the population, all four haplotypes carrying all combination of capital and small letters at both locations is possible. And if we consider this system infinitely long time, we expect that it will come to equilibrium point, where the probability of specific haplotype will be determined by the product of probabilities of specific alleles from which this haplotype is composed of. However, if these loci are very closely linked together, this process takes a lot of time, and therefore if you go to some database, for example HapMap, and pick two loci, two SNPs, which are relatively close by, most likely you will see deviation from linkage equilibrium. So this is the phenomenon which we call linkage disequilibrium. So how can we quantify linkage disequilibrium? The idea is very simple. We can contrast what we would observe under equilibrium towards what we see in the investigated population or system. And under equilibrium, we expect that the probabilities of alleles in cis are equivalent to the probabilities of alleles in trans, and this gives rise to the metric of linkage disequilibrium, which is known as D. Mathematically, if you code A capital in the first locus as 1 and A small as 0, and you do the same for the second locus, coding B capital as 1 and A small as 0, you can make a 2 by 2 table for the observed haplotype distributions, and you can see that the definition of D is equivalent to mathematical quantity known as covariance. However, D is not the most convenient measure of linkage disequilibrium because its possible maximal and minimal values are strictly defined by the frequencies of specific alleles. However, most of the time it's desirable that your measure is scaled between specific boundaries, for example 0 and 1 or -1 and 1. And therefore most used measures of linkage disequilibrium are based on D, but there is some extra component to it. For example, one of the measures of linkage disequilibrium which is commonly used in statistical genetics is R². This is basically square of the coefficient of correlation. Again, I remind you that D is covariance, but knowing the frequencies of alleles, we can scale it into the coefficient of correlation, which will be distributed between -1 and 1. And we can square it, and then the squared correlation coefficient, or coefficient of determination metric of linkage disequilibrium, will be distributed between 0 and 1, with 0 meaning no linkage disequilibrium and 1 meaning very strong or perfect linkage disequilibrium. Other important metrics of linkage disequilibrium, which is also widely used, is called Levontin's D prime. So what we do with D in this context, we are going to look up what are maximum possible values for the coefficient D under these specific allelic frequencies, and we are going to divide D by this maximum, and then again we are getting a scaled metric of linkage disequilibrium. Now we have quantified, and I defined two major metrics of linkage disequilibrium which are used, and let's think what could be the reasons for linkage disequilibrium, slightly extending on the topic which was already covered by Michel. And of course, first of all, you expect strong linkage disequilibrium between loci which are closely linked together, so they are physically very, very close. However, sometimes you see in your data that linkage disequilibrium is high for loci which are far away. And what could be the possible explanations? Well, one explanation is trivial in a way, but this is something to always keep in mind. There may be a mapping error. So actually what you consider polymorphisms which should be very close together may be polymorphisms which are actually very far apart from each other. Then other things where you will see linkage disequilibrium too high for the distance are factors similar to those which define the deviation from Hardy-Weinberg equilibrium. So these are specific types of genetic structures. For example, if in your sample you are investigating a mixture between two genetic populations, you are going to find abundant linkage disequilibrium also between loci which are very, very far apart. At the same time, if you will look into specific genetic populations within your mixed sample, you will see that linkage disequilibrium follows regular rules. So it's high for closely linked loci, and it falls very quickly to very low levels. Other factors which may, in theory, contribute to linkage disequilibrium are things like mutation and selection, but again, it's not very expected that you are likely to see it in your real data.